Okay. Hello, everyone, again. Welcome back after the coffee break, and I'm very happy that we have one more security session. So security, and this time we will speak about the post-quantum security. I'm very pleased to introduce you the three presenters, the three colleagues from the CESS project, and we will see the viewpoint from the Lukas, Malina, Hajny from the Technical University of Brno, and also from Petr Muzikant, who is currently working in Cybernetica. So, okay, without any delay, Lukas, floor is yours.
Okay, I hope that microphone is on. Good. Okay, thank you for the introduction, and I am glad to be here and talk a little about the cybersecurity in the post-quantum era. My part will be more or less about the introduction, and I will say some basic remarks about the current state of the post-quantum crypto and how it's started implemented into the current security protocols. And just a few words about the project. You already know Cybersecurity Excellence Hub in Estonian and San Moravia, and one from the 6 research challenges is also the focus on post-quantum crypto. Okay, so what is the problem actually? What are we have now? These couple of recent years, we can see that a lot of technological leaders and consortiums started to building the quantum computer. It's still something which is in the process. Definitely, we don't have like a fully functional quantum computer that can be efficient enough to crack all security stuff what we have now. But it's very dangerous, and we should be prepared. And what kind of the crypto quantum computer jeopardize? The mainly asymmetric cryptography systems which we are using every day, like RSA, ESA, elliptic curve-based schemes, and almost well-used digital signatures and asymmetric encryption schemes. Well, few slides about the current state. The Google and that consortium composed from universities started work on the Sycamore processor, which is able to work with the 53 qubits, and you can see the picture of that prototype. And then was the D-Wave company. This is the Canadian company, which are also focusing on creating the quantum computers, but it is based on the different approach. It's using quantum annealing, and what we know that these type of computers will be probably not such efficient for cracking the asymmetric crypto by Shor algorithm. Actually, they claim that they provide 2048 qubits, but they have some problems with the errors, so these type of computers probably not be efficient for cracking current crypto. And the third big group is around the IBM. You can see their plan that they started with also few qubits, and now I don't know how the project is far. They should have the Osprey processor, which is able to provide 433 qubits. But still, as we will say later, this number of qubits are probably not enough for cracking current crypto. Well, what about the algorithms? There are basically 2 algorithms, Shor's and Grover. And first, Shor algorithm was formalized in 1994. And this is the algorithm that can help to crack the current asymmetric cryptography. Well, I see a couple of papers, and I must say that there is not like the clear opinion how many qubits you need for, let's say, cracking RSA scheme with 2048 bit length parameters. Some sources claim that you need like millions of qubits. Some sources claim that you need like a couple of thousands qubits, which is like more realistic. And also recently there was the Chinese research paper that claimed that you need only like a couple of hundreds qubits, which is basically mean that the IBM Osprey processor could succeed with the cracking. But we hope that this situation is not yet realistic, because if yes, then we should like fasten the process about the migration from current crypto to post-quantum crypto more efficiently. Yeah, and the second algorithm, Groover's algorithm, that was formalized in 1996. It's an algorithm about finding more efficiently the basically keys from n brute force problem to square root time complexity problem. So that is basically the trick that if this algorithm will be on the quantum computer functional, then we need to enhance or double size all keys what we use in the symmetric crypto and what we are used in hash functions, or what we are producing with hash functions. So basically we have the two strategies, two approaches, how to be like the secure in the post-quantum era, where the quantum computing and quantum computers will be real or really functional and can crack all asymmetric crypto what we use now. Basically, quantum cryptography is quite old. The Bennett-Brassard protocol, which is used for key distribution, is known for almost 40 years. But quantum cryptography have the answers only for the key establishment. By this, you can only establish schemes, and more or less, there is not such, let's say, cheap devices. You need usually very specific equipment, and this equipment is quite expensive, and as I said, it's provide only key establishment. But the second approach, second path, is the post-quantum crypto. Post-quantum crypto is known like almost more than also 40 years, but the buzzword post-quantum cryptography is established like 20 years ago, when the first conferences were focused on this. And this is actually about finding the schemes and approaches that will just to substitute the current asymmetric cryptography schemes that have the problem with the Shor algorithm. And what is the big advantage of this path? We can already use these approaches, these schemes, on the classic computers. You don't need to do something special. Only these post-quantum cryptography schemes are usually more demanding about the memory, using the sometimes bigger keys, so you need higher memory requirements. And what is another big advantage is that post-quantum crypto can do key establishment plus asymmetric encryption plus, of course, digital signatures, and also can help with the another classical cryptographic schemes used perhaps for group signatures, threshold schemes, where is used still classic assumptions and hard problems based on the problem of factorization. So post-quantum crypto perhaps will be the new engine for wall cryptography. And also we are working in Brno on the kind of the combination of QKD systems and post-quantum crypto. So we have also own project, which is Czech project, NESPOC, so there is the link if somebody would like to check it. Okay, as I mentioned that the QKD or quantum crypto needs the special equipment, so in the picture you can see Alice and Bob. This is the equipment from ID Quantic. Actually, there are like more manufacturers that are doing QKD. The ID Quantic is perhaps the most advanced. They are based in Switzerland, and also Toshiba invest in creating own QKD systems. So we have the lucky that we have own machines in our lab. So we are playing, we are do the research, we are trying to find out some parameters, a bit how, for instance, distance between Alice and Bob affect the key rate and so on. And let's back to the post-quantum cryptography, which is actually the topic of these today's free talks. So, few facts about it. I think that a lot of you already heard about it. Perhaps there is some researchers who are working with this very intensively, doing the fundamental research and doing also applied research. So let's introduce this. Some kind of schemes are here very long, over 40 years. All these crypto try to replace the current problematic asymmetric schemes that can be jeopardized by the shore. And what about the basic families? There are actually a couple of families that provide post-quantum cryptography. The most interesting and most used family is, of course, lattice-based, but there are also another families that are also successful in the standardization, which is, for instance, hash-based cryptography and code-based crypto. The multivariate cryptography doesn't seem too much promising, as there was some problems with the security, and isogeny-based crypto is also considered that there are some problems. And few slides about the lattice-based. What is about? Lattice-based crypto usually stays on the problems like the learning with errors and ring learning with errors problem. And you can imagine that these schemes usually are based on high-dimensional grids. And the whole point is that if you are doing some small changes of all coordinates, then you are creating, when I really simplify it, some signature or some ciphertext. But this is more complicated. And also this image of the lattice is only like visualization of three-dimensional lattice, but in the fact, this is more complicated structure composed from polynomials. And yeah, there is a lot of schemes. As I said, it's very popular type of family, and all these schemes are usually answer for the encryption, key establishment. Some schemes already provide both syncryption, and some schemes are already somehow standardized by NIST. I will talk later about it. And code-based. Code-based crypto is very long. It's a very old type. It was established or proposed by McAleese in 1978. So this is it's like 45 years here. But it started to be considered now as another secure alternative to RSA, for instance. But why that was not considered early? Because the code-based crypto used and is based on a very high dimensional grid. So this is basically big matrices. So the keys then are very long, and these schemes are perhaps very fast. they are comparable, maybe faster than the classic ones like the RSA, but their disadvantage is the size of the keys. And the third promising family is hash-based crypto. I stayed with this because the NSA prioritize some schemes for signing software and firmware. So hash-based cryptography is used mainly for signing, and these types are also like quantum safe, so they are promising. Okay, there is the comparison of all families from less mature ones to the more mature. Of course, it's caused by the how schemes are here old, how long or how many was already somehow checked from the security aspects and analysis. So you can see that all ones are quite considered already proved, and some less matured have still some problems, and there is still some improvements, new schemes that need to be checked in the future. So NIST standardization a couple of years ago started with defining the new alternatives for the digital signatures and key establishment. They already selected 4 algorithms. For the key establishment, they selected Crystal Kyber. That was proposed a couple of researchers. And for the digital signature were chosen 3 schemes. Crystal's dilithium, so this is like the same family and almost the same team like for Crystal Kyber. And also Falcon, which is also lattice-based, and they already choose something different from the different family. They choose Sphinx Plus. And because they choose only one family for the key establishment, they opened another round. They will try to recommend for the standardization, perhaps something from the different family, perhaps from code-based or isogeny-based, but the SICA had recently some problems. Here, just some numbers about the key sizes and the parameter sizes. You can note that the lattice-based provide the sizes of the signatures, which are like thousands or 1,000 bytes. And if you compare, of course, to the traditional crypto of RSA, which is like the signature length is like 2,000 bits, not bytes, but bits. So you must see the difference that all these quantum cryptographic schemes, which are like promising, provide the larger parameters. Okay, so I will maybe skip it because we will also have some notes about the problems with the sizes later in the second talk. And let's focus now on the policy, what the national authorities and governments look on this problem, how they look on this problem. So in the US, National Security Agency come up with the new commercial national security algorithm suite, which is called CNSA2, and they recommend to directly exchange the old protocols or the protocols that can be jeopardized by the quantum computing by the postquantum. They are trusting to NIST, so they think that just the direct exchange will be good enough. But the European agencies are more like, let's say, conservative, and they think that we should start with the transition and we should start to hybridize and combine these two approaches, because we need some time when the post-quantum crypto will be, let's say, analyzed enough that could be like the secure. So this is their recommendation that we should, like, next 7 years use the hybrid combination, and then we can like fully translate to the post-quantum. And this is the table when you can see the comparison of CNSA CNSA 1 and 2. So you can see that already for key establishment, they recommended the selected, NIST-selected scheme, Crystal Kyber. And for the digital signatures, general digital signing, they pick the dilithium. Of course, they already recommended the highest security level, which is the 5. And what is the quite interesting that for the signing of the firmware and software, they choose the Lighten-McCallie signature and extended Merkle signature scheme, which is the hash-based. So this is quite interesting. This is the timeline, how the Americans and NSA plan to transform to the post-quantum safe. So you can see that they would like to start in next 2 years, and then after 2030, they assume that all, let's say, new security implementations should be according to CNSA 2 and prefer, of course, the post-quantum schemes inside. So in the next few last slides, I will go, I will introduce to you what is done in current security protocols. Let's start with the security protocol which is used on the link layer, which is the second layer in the network. And this protocol is called MACsec. Of course, MACsec basically encrypt data and add some authenticity tags. So there is, of course, used symmetric cryptography AES scheme. But for the key agreement, there is the MKA protocol, which should somehow establish keys and do some authentication checks. So there are currently some works that played with this and try to test some cryptographic schemes like McAleese and True, Crystal Kyber, and so on. And the results are like promising because these protocols not negatively impact the MACsec functionality, but this is still something which is on the paper in state of the art and not standardized. IPsec is perhaps more used, and we know that a couple of libraries already started to add the cryptographic schemes inside. For instance, in Strongswan library, version 6, they add into the key establishment phase the Kyber, Entry, Saber, Frodo, Dilithium, Falcon, and HQC. And there was the results that the classic McAleese, which is code-based and used the huge public sizes, are probably not very suitable for encrypted packets. And TLS is perhaps the most used protocol in the internet, right? And there are also extensive applied research where the teams try to implement the post-quantum variants and hybrid variants inside and tested the performance and the problems with the frames. So there is also like promising results, and when we start also non-standard jumbo frames, it then can help with post-quantum cryptographic transitions. And then SSH, this is also tested, and there are also a lot of works that already tested some hybrid variants, like, for instance, Kuiper plus Sphinx, and Kuiper with SCDS, and so on. And as you know, these security protocols usually used for the authentication certificates. And we know that the X.509 format certificates has some typical sizes, which are like between 500 to 1,500 bytes. And usually we use the chains of the more certificates, like the 2 or 4. So the size is like a few kilobytes. So then you can imagine that when we just to switch to the post-quantum, then we need to somehow be prepared. And there is in the red the blocks which will be affected in the X.509 format that should be somehow amended to be post-quantum ready. And my colleague Petr, Muzikant, will be continue with some practical examples about it, and he will introduce some problems. So I will just skip this slide because this is only like the survey of the well-known libraries which already providing the post-quantum crypto, and the presentations will be public, so you can check it offline. And some of these libraries will be particularly mentioned by Petr. So that brings me to the end of my talk. And now I would like to perhaps invite to Petr, who will continue my speech and the idea, and will provide you more details about the libraries. So thank you very much.
So, hello everyone. I hope the microphone is working okay. Is it? I guess so. I will wait a little bit for presentation slides. Hello, my name is Petr Muzikant, and I'm here to talk about integrating post-quantum cryptography into existing systems today. My presentation consists of 3 main chapters or parts, where I will talk about the current state of post-quantum cryptography in more detail. Then I will give a general implementation challenges, an overview over these challenges, and then I can provide some remarks and examples from our practical results. But first, a little introduction. As it was established in the last presentation, there is already some NIST standardization process going on, where we are trying to figure out which post-quantum algorithms we will use in the future. However, we have to realize that it is only the first step in actual deployment, in the process of actual deployment in real-life IT systems. So this has been the main inspiration behind our work, where we have been focusing more on engineering aspects of post-quantum protocol implementations from more like a developer's point of view. So we are trying to explore the current options and provide some hopefully helpful remarks and tips. Okay, so let's go to the current state of post-quantum cryptography. First, I have a list of some featured libraries that I would personally recommend to check out first when we are trying to implement post-quantum cryptography, let's say, in your applications. So the first 2 are actually pretty similar in what they do. They provide a aggregated list of NIST-submitted algorithms, so not only those that are currently going to be standardized, those 4 that Lukas has talked about, but also some other. And they are providing those under unified API. So it is quite easy to implement the first algorithm and then implement others later. But that's where the differences are actually, that's where the differences begin, because the PQ clean, the first one, is pretty low level. It's so low level that it can't even be called a library, because the authors actually encourage you to download and copy the code into your project yourself, build it, compile it, build it, and use it in your project as a code. On the other hand, the libOQS, which is from Open Quantum Safe organization, which is pretty active community, open source community in this area. It is much higher level. It is a standalone library that you can build, add it as a dependency to your IT system and project, and work with that. They also provide a lot of wrappers for various programming languages, so it is quite easy to use in other projects other than C, other than those written in C. And they also provide some applications built with this library. So as Lukas already mentioned, there are applications there are quantum safe, let's say quantum safe versions of OpenSSL, OpenSSH, and OpenVPN, etc. There are also some language-specific libraries, like a Bouncy Castle for Java and C#, or even some platform-specific libraries that are optimized for specific chipsets. Like here, a PQM4 is optimized for ARM Cortex M4 chipset, if you want to run it on some embedded device. Then we move to ASN1 structures, which are actually pretty essential when you are working with cryptographic objects in your application. However, there are no standards yet to exist, so even the NIST standardization process requires authors to only input and output raw data. And however, the attributes and some values that are internal to that algorithm, it's completely hidden out of NIST's point of view. Fortunately, there are some multiple RFC drafts that define these structures. However, it's pretty incomplete and it's subject to change because it's still an RFC draft, so I wouldn't really recommend relying on that. This is where the first complications actually begin, because there are already some differences in PQ libraries. Like already mentioned, liboqs, it follows this NIST rule and operates only on raw bytes. And the bouncy castle, on the other hand, is trying to be a little bit more fancy, and it's already incorporated these ASN1 structures to their code base. So as a developer, you have to work with that. Another problem is with object identifiers, where they were basically non-existent, so the Open Quantum Safe community needed to create their own, and Bouncy Council expanded on that. Then we have JSON web algorithms, which are another way of working with cryptographic objects, particularly on the web. In the JSON web signature scheme, you are actually, there are usually identifications for digital signature and hash at the same time. You have an example of ES384 on the slides. So what's the deal with post-quantum JSON web algorithms? Well, again, there are no standardization and even no RFC drafts here. There is only one RFC draft for JSON web encoding, which is something similar, but it only defines the identifications for digital signature. And there is no hash. So what to do when your application is used to working with hash identifications as well? Well, there are basically three options. You can either always use, for example, SHA-512, or you can expand the JSON web encoding with a number, which will be identifying the hash function, or you just wait for another RFC. Last thing from this chapter is a hybrid mode, which is a combination of post-quantum cryptography and classical cryptography. As it was already mentioned, it basically ensures the protection against quantum computers in the future, and at the same time protects against some emerging threats that may or may not come in the following years on currently discussed post-quantum cryptographic algorithms. There are two most common modes that you might encounter. There are concatenation and sequential modes. You either put two digital signatures together from different cryptography families, or you can use an output of one digital signature as an input for another digital signature. However, both of these modes have their own issues, so there is nothing concrete yet. I would personally recommend the concatenation mode, since it is the mode that was chosen by Google Chrome developers recently for their own experimental post-quantum TLS configuration. Now we move on to some general implementation challenges, or in other words, the stuff that is good to know when we are trying to implement post-quantum cryptography yourself. First, I would definitely recommend to identify relevant locations in your code base. You can do it by identifying all the public key infrastructure objects and tracing their data flow from the start of their lifetime to the end of their lifetime. It is also good to be aware of maximum transmission units when transferring these objects between different components, because as it was already told, these objects usually have bigger sizes and even variable sizes, which can mess up your applications when they are not prepared for it. And last thing, you should be also aware of changing data formats between different components, so they know how to communicate with each other even after you change to post-quantum cryptography. One thing to actually, which is pretty helpful here to incorporate all this information into one diagram, is a BPMN diagram. As you can see here as an example, I have 3 different components in 3 different lanes. And each lane and each component has its own operations and data that it is doing its operation on. So by red notation, we have marked some specific places that will need to be post-quantumized, or that will need to, as you will need to implement post-quantum support in them, as well as in the form of comments. We are noting the data format in which the data is stored, and also some maximum transmission units between components. So it's pretty helpful to start from here. Another thing, technological constraints. You should always assess the boundaries of your current system that you are trying to post-quantumize. You should count with increased performance, memory, and storage overhead. This is especially true on limited devices and slow networks, so be careful of that. So just to sum up, I would recommend to start at the beginning of data lifecycle and implement the post-quantum support one step at a time. This really helps to keep things in track. There is very high probability that your current cryptography library will not be able to work with post-quantum cryptography, so some extensions and complete swaps will be required. In that case, you can use softwares like SWIG, which is a wrapper generator for C libraries, from C libraries to another programming languages. I will talk about it in a couple of slides. So now we move on to the last chapter, which are practical results, remarks, and examples. These are basically gathered from an experience from the last two projects we have been working on. I won't be going into any much detail about these projects because the following slides, basically those remarks and examples, are much more important in the context of this presentation. So first, we have been working on a post-quantum authentication framework, which can be considered as our first proof of concept in this area, where we have three different components. We have a web service, we have an authentication framework, and we have an authentication user device in the form of embedded device. Together, these three components can create an authentication result based on dilithium or Falcon signatures, which are the two to-be standardized digital signature algorithms in this in post-quantum era. And as you can see in the picture, it actually consists of multiple low-level components that needed to be adjusted for post-quantum support. So what have we learned from this project? First of all, even devices that are more capable than let's say, smart cards are still problematic. In our case, we were limited to only 8 kilobytes of stack memory. It was due to used operation system on the device. And as it turns out, the PQ clean, where we copied the code and put it inside the device, it allocates to stack a lot. And by that, I mean everything is in stack. So after some troubleshooting, we have decided to just modify the PQ clean code and move everything to heap memory, while making sure that we are keeping the memory safety intact, as well as the algorithm logic itself. Then we have learned something about libOQS extensions, where, okay, I told you that there are a lot of programming language wrappers, but the one that we really needed was in PHP, and it was missing. So we have turned to SWIG wrapper generator, where it is pretty easy to you just need to implement one C or C++ interface, and the SWIG actually generates everything for you almost automatically. So by that way, we have created a wrapper for PHP, and while we were at it, we also created a Python just to get some more experience. Just some note, there was some type remapping required, but it wasn't really a big deal. Next, I want to talk about post-quantum usage in PHP itself, because usually you will find that a lot of, let's say, PHP servers are actually using, for example, the OpenSSL, internal functions for OpenSSL, which is using the OpenSSL that is installed on the machine. So we have also tried to install the OpenQuantum Safe fork, which is supposed to work with post-quantum algorithms. There are basically free versions on how to install it. I won't go through all of them, but I would just recommend the last one. which is actually the way where you are building only the provider that can be injected into a vanilla OpenSSL, which is much more easier and without any pain, I would say. Another high-level library that is commonly used is a PHP cyclib. We didn't find any post-quantum support there, so we have created our own fork, and internally we are using those two options mentioned before. Next project was from CDoc2. It is a specification for securing and exchanging encrypted messages from sender to receiver. For those who know something about cryptographic message syntax, or CMS, this might sound pretty familiar because it is used in almost the same use case, I think. The problem is that the reference implementation in Java only expects and is working with RSA and EC or symmetric keys. So we have expanded this project with the ability to accept also crystal Kyber keys. This basically required to update the bouncy castle version and follow the RSA and EC algorithms objects lifetimes and implementing post-quantum support for Kyber one step at a time. So in this project, there are also some remarks, but most of them are on bouncy castle. Because even though it's pretty popular and well-supported library, the post-quantum capabilities in this library is very, very poorly documented. And by that, I mean it's not documented at all. All you have are some packages, API references, and if you are brave enough, you can also look into the source code, but that's not really a recommended way of working with this library. Another drawback was already mentioned that it's using the ASN drafts, which I would say just only complicates things for the developer. Since our experience from this project was mostly trial and error and trying to put some code together, I have some code examples here, but I won't go over them in any detail because it's there only for you if you are interested in this and you want to try it yourself later at home, so you can go back to this presentation and even copy the code because it is now tested and hopefully working. So here we have some code example on how to actually inject this post-quantum cryptography provider into the Java security package. Then we have a key pair generation, a key encapsulation, and key decapsulation. So again, if you want, you can go to the slides later. Two more things in this project. One is a complicated TLS client certificate usage because when we add a key exchange server into this project, into those scenarios in CDoc2, which are part of the specification, so it's nothing new, there is a problem that the internal SSL implementation is having a big problem with certificates that have a Kyber key in them. It basically didn't allow any even creation of that TLS connection. So we have bypassed this by injecting the Kyber key into a specific X509 extension, which is called subject alt public key info, which basically allows you to insert another public key into the certificate. So by that way, the Java SSL implementation didn't really have any problems because it did all its validation and checks on the original subject public key info. And the last thing, if you are working with bouncy castle in Java, you will most probably be working with a Java key tool, which is a command line tool for managing key store with cryptographic objects. So I just have this slide here to actually show you how to inject the provider into the key tool as well. And the last project, I don't have any remarks from that because it didn't happen yet. This is maybe the most interesting out of those three, where we are trying to ensure the quantum safety of electronic voting process that is currently used in Estonia. However, this will require some more time-consuming research because we cannot just drop in the currently to be standardized digital signatures and key encapsulation mechanisms because there are much more advanced cryptographic primitives at play in this scheme, such as asymmetric vault encryption, mixed nets, and zero-knowledge proofs. So we will see how it goes and what will come out of it in the following months, let's say. So to conclude, I would say personally that implementing post-quantum cryptography today is definitely possible. It is complicated. It is possible but complicated, but it is hella worth of try, because it is, I would say it's better to be prepared than before it's too late. And also the post-quantum cryptography open source world or community is pretty dominant. So it is, I would say it will be worth it to at least try to support it and keep its dominance. Okay, so that's all from me, and I will give my word to Mr. Hajny for the next presentation. Thank you.
So hello, everyone. Hope you can hear me well. I don't have a full presentation. It's just a short remark with a couple of slides. But before I start, I need to thank the organizers for letting us speak here. You have a beautiful university and beautiful city, so thank you very much for that. You heard already from my colleagues about post-quantum crypto. You heard something about the theory, a little bit about the libraries we have. And here now, I would like to give you a toy, something to play with if you are interested in post-quantum cryptography. I will be presenting a project, a student's project, which started around 1 year ago, and now it's evolving into, let's say, a standard research project. It's called, the presentation or the slides are entitled Linux Encryptor of Network Traffic, and the basic idea is to create an encryption and decryption device which is quantum safe. So using only cryptography based on the problems that cannot be attacked by quantum computers. Okay, so as I said, we are trying to create two gateways that are able to take network traffic, which is unencrypted, encrypted, and then send it through some insecure network, and on the other side do the opposite, so decrypt and send the data to the internal network. So yeah, so basically these blue devices are our target, our goal to create. We are mostly using post-quantum crypto. For encryption of the data of the network traffic, it's easy. As already Lukas mentioned, the symmetric crypto with long enough keys is still safe. So we are still using the standard AES cipher with larger keys, 256. That should be safe even if we have quantum computers ready. On the other side, for the key agreement, we cannot use these standard mechanisms like the Diffie-Hellman protocol. We need to use the post-quantum algorithms. So currently in our project, we are using the Crystal Kyber, the candidate for the standardization by NIST. That's the post-quantum part. For those of you who have already some quantum devices at home for the key agreement, we also do support the use of quantum-generated keys, the QKDs. Currently, the Linux machines, the encryptors have the support for ID-quantic machines, which we have in the lab. So that's why we are using both post-quantum and quantum keys to create a hybrid key which then encrypts the traffic. The properties, how it works. So basically, we take the TCP packets of the network traffic, we encrypt them and encapsulate them into the UDP datagrams and send it through the network. And then on the other side, we decapsulate from UDP datagrams, decrypt, and send the traffic to the internal network. It's simple, but it turned out that it's also efficient. we don't have to care about some lost packets and so on, because inside UDP there is still the TCP connection, which is dealing with all the problems of lost packets and so on. Currently, it's completely a software solution. So we are using standard Linux virtual machines with 2 interfaces. One is the input of the traffic. The other one is the output for the encrypted part. It's basically the whole project is a small script that can be run in like 5 minutes. So as I said in the beginning, it's a toy example to play with, to have the first experience with the post-quantum crypto. So here you can see the algorithm we are using. As I said, for the encryption, it's AES. For the key agreement, it's either post-quantum crystal Kyber or the standard quantum device, which usually is not available at many laboratories. For the combination of the post-quantum and quantum key, we are currently using just simple hash function, SHA-3, but we have also some research activities in more advanced way of combination. Currently, we have a paper submission. We are waiting for the reviews, if it's worth something or if it's a crap. Here's a little bit about the packet structure. As I said, we take the packet, encapsulate, and send it via UDP. So nothing difficult. There is one problem with the encryption. We cannot use the keys forever. After some amount of data transmitted, we need to rekey. In this case, these encryption machines just ask the quantum key distribution devices for a new key and also run the post-quantum key agreement protocol to create a new post-quantum key and then replace the key for the encryption. In this process, we always lose some of the packets because there is a short moment where the machines have different keys. Different key for encryption, different key for decryption. But still, this does not have to be resolved with some more difficult management, because with TCP, the machines will ask for resending, and then we will get the packets encrypted by the new key. So the TCP solves a lot of problems in this case. Regarding the performance, as I said, it's a student project, so it's not very highly optimized. It's running on multiple cores, so there is some multi-threading, but still we are able to thank you. We are able to go to around 100 megabits per second. Without encryption, we were able to reach around 470 megabits. So you can see that there is a significant loss of performance due to the encryption, but still for playing 140 megabits is okay. There is also another fork of the project where we implement the same thing on hardware in VHDL. And in that case, everything is accelerated by the VHDL, by the FPGA chip. And there we can go up to 100 gigabits. So in the software, we don't really need the performance. If somebody is interested in high performance encryption systems, we have the version on the hardware. Everything is open. Everything is on GitHub, so as I said, the installation is extremely easy. The main purpose is to attract you and to give you the links for playing with the project. The installation usage is really very easy. We will soon also put a video how to create these encryptors and how to test them on a real network. So you are more than welcome to join us for the project. If you are administrating or supervising students' project, please feel free to propose this as a project for semester or maybe diploma thesis. We are also open to any way of collaboration through the Erasmus and so on. There is an agreement between the Tartu University and the Brno University of Technology. So we would be very happy if you propagate this small toy to the students. For the summary, I think it should be clear now. Software encryptor available on GitHub. Feel free to join us. Thank you so much. It's all from my part.
Okay, so now we have heard all three presentations, and I'd like to invite all three presenters here. And, well, I open the floor for discussion, for questions.
Hi, thank you. I just wanted to ask about the very first part where you talked about like upcoming quantum computers, but these are like physical qubits, not like logical qubits. The Osprey and what was it, like 400? But these are like physical qubits, which I don't think they translate to logical qubits that well. So actually, we are like further from actual like factoring, or is this not correct anymore?
Sorry, if I understand well, so you are asking about the number of physical qubits which can jeopardize RSA, or you mentioned that the research from the Chinese team?
I was not quite sure whether the Osprey thing, that's like physical qubits, right? And I haven't like kept up with the thing, so like last time I remember that physical qubits and logical qubits are actually like quite far apart. So does this mean that actually the 466, or like what was it? Is it like physical qubits? And does that mean that actually we are like further away from actual attacks or factoring than it would seem?
Yeah, maybe I can step in. Yes, those 400s were physical qubits, and that's very far away from the logical qubits, which can cause any attack. So we should be fine.
Okay, thanks.
For now.
Okay, anything else? Anybody else? Okay, it means I also have a chance to ask my question. Well, I would like to be a very naive and to have maybe a very simple question, but let's put it this way. And now we hear like about quantum computing and post-quantum security a lot, but still it is like on the research test out stage. When do you think it will become really like real life?
Okay. Well, nobody knows what will be in future. Some researchers claims that it will be not in our lifetimes, but there is also some estimations that perhaps in next 20 years this is actually the real problem, and having all effort into the post-quantum cryptography will be finally probably worth for and used in the practice.
Even more naive question. How large is the quantum computer at the moment? Physically?
How big? You mean like one big room? I would say.
One big room. So something reminds me like the 50s.
Yeah.
We have normal computers.
2 to 3 meters on the right. Yeah, so that was the picture of that of the prototype from IBM and from Google, and there is a lot of like obstacles to building such kind of device, and you need a board really with the specific physical things, and for instance, you can also cooling this device to absolute zero, at least in one of the approaches. And yeah, for instance, there was also the example of the D-Wave from the Canadian, and the cost is like 15 million US dollars. But on the other hand, they claim that they don't consume too much electricity, so it's more efficient than some kind of supercomputer which also like takes the rooms.
So if I may, one short remark on the future of the quantum computing. I don't think it really matters if we have the quantum computer in 5 or 10 or 15 years, because the data we are sending now can be stored and maybe of some value to the attackers even after those 15 years. And if they store it now, we cannot change the encryption mechanism. So if something is vulnerable, let's say in 10 years, they will wait. And after 10 years, when we have the quantum computer, they can decrypt. So that's why even if the attack is not so close, if the computers are not there, there is a real reason to go into the post-quantum cryptography because of this problem of storing the data.
I think that based on what we know, and you have mentioned the 50s, so we know how the technological advance is going forward. We can be almost sure that this classical cryptography will be broken eventually. So you mentioned the post-quantum research. So I would argue that if we know that it will be broken sometime in the future, it's better to start researching it harder and more efficiently sooner than later.
Thank you. Any other question? If not, then I'd like to thank again the presenters.